Hello friends, we start with our next topic that is known as concepts of capacitors and inductors. Till date we have completed about the operational amplifier. Now we start with our next very important topic of networks, that is known as concepts of capacitors and inductors. You will find there are a lot of applications of capacitor and inductor in your communication subjects, also in your analog, EDC, everywhere. So here we will understand the concepts which basically pertains to networks analysis. Okay, you will find the application of these capacitors also in your first order and second order initial conditions. So we start with this topic. If still you have not subscribed, comment and like my channel. Please subscribe it, please comment it, please like it, because once you subscribe it will be more easy for you to go through my all videos in a sequential manner. The link of my previous video is already mentioned in my description box. Please go through it and please try to understand all those topics. So we start with our next topic, that is known as concepts of capacitor and inductor. So first we talk about capacitor and then we will talk about inductor. So first I will take it as capacitors. Now friends, you will find, as I said earlier, there are a lot of applications of capacitors. So what is capacitor and how it acts, and how the problem used to come in your examination from capacitors, we will see. Okay, so capacitor, first of all we'll see it is represented in this form. These are the two plates. Between these two plates some dielectric is existing. Okay, and when it is connected to some potential, say this is potential V and I call it as C, and let some current flowing is I. So this is the condition of a capacitor, in which we will see the capacitor is represented by C. The unit of this capacitor is known as farad. What it is? Farad. Now we will little bit understand about the capacitor, what actually it is. If I draw one diagram, little bit we will understand the concepts of capacitor. So friends, these are the two parallel plates which is placed with some distance d, and the area of this plate is A. Now capacitor means there are the two plates which kept at some distance, that distance is d, and between these two plates there is some dielectric. Okay, dielectric is another concept, or you can say dielectric is another term. We will see dielectric means a kind of media. It's a kind of media which may be an air, which may be a mica, and which may be any medium which starts polarizing when a voltage is applied between these two plates. So for the time being, you can say the medium which is existing between these two plates, I call it as dielectric. What it is? Dielectric. So from here we will see that when voltage V, for the time being we will take a voltage V is applied with some current I which is flowing. So this arrangement, these are the two parallel plate which is kept at some distance d, having these plate which is having a cross sectional area of A. So under this condition it was given that Q is directly proportional to V. What is this Q? Q is known as charge. Q is known as charge which is accumulating at the plate of the capacitor, and Q is basically dependent upon what? Is depend upon the voltage V. It means whatever the voltage is applicable on these two plates, there is an accumulation of charge at these two plates. Okay, so if I remove this proportionality constant, there one term used to come that is known as C, and this C we will call it as a capacitance. What we will call it is a capacitance. So from here you can say that the value of C is equal to Q by V. The value of C is equal to Q by V, or you can say the unit of Q is Coulomb upon volt, and it is known as Farad. Okay, this is known as Farad. So the unit, this is a unit of capacitor, which is known as Farad. Okay, so there are different Farad is a big unit of capacitor. We will see, we always talk about millifarad, microfarad, or you call it as picofarad. So there are different type of units of capacitor, and you will see millifarad, microfarad, picofarad. Milli means it is 10 to power minus 3, it is 10 to power minus 6, and it is 10 to power minus 12, like that. So we will see in this form, we will analyze the different type of capacitor values. So as I said, Q is directly proportional to V, so Q is equal to CV. That means finally you can say that the C is given by Q by V. This is all about the capacitor. Now when we comes to the point that yes, the value of Q equal to CV, that means C is equal to Q by V. So you can say that by increasing voltage the value of capacitance is decreasing, or by increasing the charge the value of capacitance increasing. But please keep in mind, this C does not depend upon Q and V. Why? Because it is a constant factor and its value is depend upon some other value. Okay, and basically the capacitor is given by epsilon. You can say here it is epsilon A by D. This is the formula for capacitor, just keep in mind. This epsilon is known as dielectric, as I mentioned here, or you can say it's a dielectric constant, or it explains the permittivity. Okay, and this A is the cross-sectional area of this plate, and D is the distance between these two plate. Okay, so you can say that the value of capacitor mainly proportional to the area and inversely proportional to the distance between the plate. Okay, just keep in mind. Okay, so the value of capacitor is mainly dependent upon the area of cross section and the distance inversely proportional to the distance between the plate. That means if you increase the value of D, the capacitance will decrease, or if you increase the value of A, the capacitor value, that is capacitance, will increase. Okay, so this is all about capacitor. Now little bit we will try to understand more the concept of capacitor. Okay, you'll see. Now friends, we will see the more concepts of capacitor and we'll try to understand. As I said earlier, this is a two conducting plate, and between these two plates there exists a dielectric. We call it as dielectric. Okay, this dielectric may be an air, maybe mica, maybe an insulator, and so on, depending upon the property. Okay, so here we'll little bit discuss about the working of the capacitor. You might have seen that working in your in other EDC subject also, but for the time being we will little bit will try to understand it. As we know that when a voltage V is applied across the capacitor, initially these plates are neutrally uncharged. I mean, I can say that the plates are neutral in nature. The plates are neutral in nature. That means this plate carry equal number of positive and negative charges. If I say here, you can say that if these are the positive charges and these are the negative charges, so if I talk about these plates, these two plates are the conducting plates, so you can say that this plate is having the neutral charges, that is plus minus here also and here also. Yes, but when this voltage V is applied, say this is the polarity plus minus, when this voltage V is applied, what happens? whatever the electrons here will start attracting towards this voltage. That means if these are the electrons, so it starts attracting here, and now these electrons are flowing in this fashion. So yes, you can say that there is a current which flows start in this manner. But the point is, a question comes to your mind, how the current will flow here? Because from here to here there exists a dielectric media. So just keep in mind, this media is having, we call it as polar molecule. It is in the form of polar molecule. If I draw this, it is in the form of this. Okay, these are known as polar molecule having positive, negative, positive, negative. We call it as polar molecule. If I draw here, it is plus minus, plus minus. Okay, so this is known as polar molecule. So when this voltage is applied, what will happen? These polar molecule will align, and it align in this manner. Okay, it align in this manner. When this positive is applied, here it is minus plus, minus plus, minus plus. In this manner, these molecules get aligned. Okay, and some current will start flowing here, or you can say that current is known as displacement current. This you will more learn in your EDC subject. For the time being, I am explaining here. This current is known as displacement current. Okay, so the overall you can say that yes, when this voltage V is applied, and because of this electron flowing in this manner and these polar molecule get aligned, there is a flow. That flow is known as displacement current within this boundary, and finally you can call, yes, some current I will flowing start in this manner. Okay, now one more important thing is how this how here these molecule get aligned. It is because of development of electric field between these two plates. Okay, the electric field will develop between these two plates. How? Please see. If these are the plate, as I said, when electrons start flowing in here, the positive charges will remain here. Okay, more number of positive charges will accumulate at this plate, and you can say that more number of negative charges will accumulate on this plate. Okay, so as this density increases here as well as here, a potential difference is developed between these two plates, and we call that potential is basically denoted by E, that is known as an electric field will be developed. Because of this potential difference, an electric field is developed, and we call this E is V by D. That means from here to here one electric field will be developed. Okay, and because of presence of this electric field, yes, a current starts flowing, and now you can say that the value of this electric field is depending upon the V, that is the voltage which is applied across this plate and the distance between these two plates. So yes, electric field will definitely increase when the voltage is increased, or you can say when the distance between the plates is decreased. Okay, and yes, once the electric field results here, as I said, some current will start flowing, and that current is known as displacement current, and in this way the capacitor starts working. So now a question comes to your mind that yes, by increasing the value of V, one can easily increase the value of electric field, and by increasing continuously the value of V, we can increase the electric field. Okay, or as I said earlier, Q is equal to CV. From here you can say that V is equal to Q by C. It means by increasing voltage, your charge will get increased. Okay, is it like that? No, the very important thing is, once you apply a voltage across this capacitor, there should be a limit of this plates. Okay, and if that limit is crosses, that plates get ruined, or you can say these plates get destroyed. Okay, so these plates are having a specific voltage level. We call that voltage is known as breakdown voltage. Okay, that means you cannot increase the value of V just to increase the electric field. It means your capacitance, your parallel, these two plates, that is these two insulating plates, are now restricted by a voltage, and that voltage is known as breakdown voltage. So just keep in mind, every capacitor is having some breakdown voltage. Every capacitor is having some breakdown voltage. You cannot increase that voltage above that breakdown voltage, otherwise that capacitor will get destroyed and it does not work. That's why in earlier I already mentioned you about the value of capacitance, that is epsilon A by D. With the help of this value, one can able to increase the value of capacitance. Okay, so it doesn't mean that just by increasing voltage you can continuously increase the value of electric field and thus result in a more capacitive value. It is not possible at all. The value of capacitance C is mainly dependent upon the value of epsilon A by D, by increasing the value of area or by decreasing the distance between the plate. Okay, so this is all about the capacitor. Now we will see what more important concept is required to understand in capacitors. Now, as we know that the value of I is dq by dt, if I consider a capacitor is having current I, capacitor is C, and this is a voltage V. So we know that I is dq by dt and the value of Q is CV. So you can say that the value of I comes to be d by dt, that is C into V. Okay, so from here you can say that it is C dV by dt. This is the value of I, that is the current across the capacitor. So you can say that the value of current across the capacitor is a differential rate of voltage. Okay, so this is the current across the capacitor. So from here you can say that the value of V is 1 upon C integral of I dt, and this is the value of voltage across the capacitor. So these are the two important formulas. From here we will see that the value of V is, you can also write it as 1 upon C integral minus infinite to t dt, or you can write this value as 1 upon C integral t naught to t dt plus of V t naught, because we know that once we go for integration there is a constant and this is your constant. Okay, so you can say that the voltage across capacitor is having some initial voltage. We call it as initial voltage. Or we say that a capacitor is having some memory. Okay, a capacitor is having some memory. This we will try to understand more through this concept. Just now I told you that these two plates, here were the positive charges, accumulation of positive charges, okay, and here were the negative charges. Now what happened, until unless a voltage is applied, when the voltage is applied, this plates get charged, and when you remove this voltage which is applied here and just remove by some load resistance, say that load is R, or you call it as a bulb, for the timing you call it as a bulb. What will happen when you replace this, a current again starts flowing from here to here. Okay, that means this electrons will move in this fashion and it is attracted by this positive charge. So that's why some current will start flowing in this fashion. Okay, so that means the capacitor plates which are initially charged by some voltage, when some voltage V was applied, as I earlier mentioned in my diagram, that plate will get discharged when some load is connected. So definitely there a concept comes known as time interval. This we will more understand in our initial condition, but for the time being you just try to understand that there is a time interval. Say this is some time interval, this is some time interval. If I call this as T naught and this as T, so when it was at T naught, the capacitor having some charges, but when we are talking about T, these charges will get discharged through this load. Okay, so that's why capacitor is having some initial charge and we will call it as Vt naught, or you can say some initial memory. Okay, so and in this manner the energy transformation will take place. That's why we call it as the capacitor will not dissipate the energy, rather it stores energy, and at the time of when it is connected in the network, it delivers the energy to the other load. Okay, so the capacitor will not dissipate the energy, rather it stores the energy. But now a question comes to your mind that this is a kind of ideal capacitor or it is a practical capacitor. So now again the another term used to come here is known as ideal or practical capacitor. We will see that also. If this is your capacitor, so generally we are talking about the ideal capacitor. So this is your ideal capacitor. Okay, but when you talk about the practical capacitors, this capacitors is in this form. Again this is C, this is C, and this is your resistance R, and we call it as practical capacitors. Okay, in case of ideal capacitor, this value R is in the value of 100 of mega ohm. This value is in the order of hundreds of mega ohm. So for your all application, generally we will not consider this value R, and that's why because of this high value of R and therefore because of this high value of R, we generally remove that value. Okay, so this is your ideal capacitor and this is your practical capacitor. Okay, now if we talk about in networks we always consider a capacitor to be ideal in nature. Okay, so as I told you, I is equal to C dV by dt. So when voltage V is applied, now if I talk about this is a DC voltage, if I talk about this is a DC voltage, so that means V is constant in nature. And if V is constant in nature, if you find the differential of a constant, that is d upon dt, that is a constant function. Yes, V is what, as I said, it is a constant function, that is constant V. So the value of I comes to be 0. Okay, the value of I comes to be 0. That means no current will flow. So you can say that capacitor at DC behaves like an open circuit. Very important. Capacitor at DC behaves like an open circuit. Just keep in mind. Okay. At DC, capacitors behaves like an open circuit, and the same concept is used in your networks. Okay. So till now we have seen various formula for the capacitor. Once again I will list all those formula. First, that is the current across capacitor is given by C dV by dt. Similarly, the voltage is given by 1 upon C integral I dt. Or if I talk about the limits, so it is 1 upon C integral minus infinite to T dt, or you can say it is 1 upon C integral T naught to T that is I. Okay, it is I dt plus of Vt naught. Okay, we have seen the value of C, that is epsilon A by D. We have also seen the electric field across the capacitor, that is E V by D. This is our first formula, this is second. I am just summarizing. Similarly, there exists an energy across the capacitor represented by Wc, and its formula is 1 upon Cv square. I am not going in derivation of all these. So just keep in your mind, this is your first formula, this is your second formula, this one is your third, this one is your fourth, this one is your fifth. Here this unit is in farad. Okay, this you know, it is in ampere, it is in volt, it is in, that is volt per meter, and this is in joules. Okay, so this is all about the formula which we have seen in capacitor, and you must remember these formula, because we will see while solving the networks, we will try to understand these formula and will apply these formula to solve the problems. Okay, we will see few more basic concepts which is applicable in networks. In my previous topic, that is known as op-amp, I told you about two important things known as integrator and differentiator. So you will see integration and differentiation is a mathematical operation. It is possible with the help of use of capacitor. Okay, but in case of operational amplifiers, how it is used, just try to understand. So here are the two circuits. This is your 1 and this circuit is your 2. Okay, so now just try to understand the position of the capacitor. When capacitor is connected in a feedback pattern, when capacitor is connected in a feedback pattern in an op-amp, it is referred as integrator. Very important, just keep in mind, it is referred as integrator. Similarly, when capacitor is connected in this fashion, not in feedback, so this is referred as differentiator. Okay, it is referred as differentiator. So these are the two important I can say these are the two important diagrams and the way through which we will solve the numerical problems. So you just keep in your mind the position of capacitor once it is connected in feedback pattern. So it behaves like an integrator, and if it is connected in this fashion, so it is an differentiator. Generally, if you talk about this type of configuration, because we will see the application of integrator is maximum in any type of subjects like your EDC, ADC, anywhere. Why? Because this integrator is basically your low pass filter. It behaves like a low pass filter, and you will see there is a large application of low pass filter. Okay, low pass filter, it means passes the lower frequency. Okay, so and similarly this differentiator behaves like a high pass filter. Okay, so there is a lot more applications of low pass filter in your EDC and ADC. That's why integrator is mainly used, and most of the problems you will see based on this type of configuration. This is not directly used in this fashion because of high gain of operational amplifier, and that's why some resistance will introduce here to control this gain, so that your entire integrator work in a proper manner. Okay, so this is just a basic concepts you will more understand in your analog devices and circuits. But for the timing, I have just mentioned you that yes, the integrator having a lot of uses and lot of applications in networks. Okay, and this is all about the differentiator. So little bit we will see the I can say the relation between the output voltage and input voltage in both the case, that is in integrator as well as in differentiator, so that one can easily understand how it acts like an integrator and how it acts like an differentiator. Okay, as I said you earlier, whatever the op amp we are considering here, these are ideal in nature. Very important thing, these are ideal in nature. That means no current will flow here, and when no current will flow here, whatever the potential here will appear at these two nodes by the concept of virtual ground. So if I is flowing here, that means the same I will flowing here. If this is the current I which is flowing here, the same I will flow here. So just by applying the law of KCL, one can easily find the relation between the input and the output voltage. Now if you see from here, if this is a potential at ground, so the voltage here is 0 volt, similarly the voltage here is 0 volt. So can we find the relation between V0 and Vi by applying KCL at this node? Yes. So I am applying KCL at this node. You can say that 0 minus of Vi upon R1, okay, plus, now see, the current across the capacitor, as I mentioned you, is I, that is C dV by dt. So from here, can I say that the current here is C d upon dt? The voltage here is what? It is 0 minus of V0. Yes, 0 minus of V0, that is equal to 0. Can I say in this manner? Why? Because it is 0 minus of V0. This is your positive potential. I can say that it is further connected to ground. So it is in this manner. So when you apply a loop, it is 0 plus 2 minus again minus. So it is 0 minus of V0. So from here you can say that Vi upon R1 is equal to minus of dV0 upon dt, minus of C dV0 upon dt. Yes, minus of C dV0 by dt. And from here you can say that dV0 upon dt is equal to minus of 1 upon R1C into Vi. Okay. So from here you can say that the value of V0 is equal to minus of 1 upon R1C integration Vi into dt. Yes. Yes. So this is your equation, that is dV0 dt is equal to minus of 1 upon R1C Vi. From here you can say that dV0 is equal to minus of 1 upon R1C Vi into dt. If we have to find the value of V0, we have to integrate it, and once you integrate it, that comes to be minus of R1C integration of Vi dt. So from here we just identified that the relation between output and input in this form. So you can say that your output is the integrated form of your input, and that's why this is called as integrator. That's why it is called as integrator. Just keep in mind. If it is connected in this fashion, so we call it as differentiator. Now what it is differentiator. Previously it was integrator, now it is differentiator. How? Now please see again with the concept of virtual ground. Since op amp is ideal in nature, no current will flow, whatever the voltage here, it is 0 volt, will appear here. So if I apply KCL at this node, KCL, so that comes to be 0 minus of Vi, that is C dV upon dt. Okay, the current in this branch It is what? C d upon dt 0 minus of Vi plus of 0 minus of V naught upon R1. That is equal to what? 0. Yes. Here is the current is what? That is C dV by dt. So it is C d upon dt. What is V? It is 0 minus of Vi. Simply I put here plus 0 minus of V naught upon R1. So from here you can say that minus of C dVi by dt is equal to V naught upon R1. So from here you can say that the value of V naught is equal to minus of R1C into dvi upon dt. So this is another relation between V naught and Vi. From here we analyze that our output voltage is the differentiation of our input voltage, and that's why it is referred as differentiator. In both the condition, that is in integrator as well as in differentiator, we have seen that whatever the input we have applied, it is at the inverting terminal, that is at the negative. So the voltage here comes to be what? It is minus of R1C dV by dt. In case of integrator, what was the voltage? Once again I am writing this expression. It is V naught is equal to minus 1 upon R1C integral Vi dt. Okay, so this was the case of integrator and this is a case of differentiator. Okay, so this is all about capacitor when connected in this fashion and when it is connected in feedback fashion. Okay, the voltage and current divisions rule. This is also applicable and we will see how it is, how we will solve it. So friends, these are the two cases, case 1 and case 2. Here I am talking about voltage and here I am talking about current. So basically this is a current division and voltage division rules. Okay, so we will see one by one both the rules. When such type of situation is there, in resistance we have seen, okay, in case of resistance we have already seen. If I just take an example of resistance, okay, if this is a voltage V, this is R1, R2, say some voltage V2 here, say some voltage V1 here. So you directly write V2 as V. If I take it as Vs, so Vs into R2 upon R1 plus of R2. And similarly you can find the value of V1. But this is the case of resistance. Okay, this was the case of resistance. But when you talk about the capacitance, that is capacitor, so here I am directly writing the formula and then we will see how we have find this. The value of V1 and V2, the value of V1 comes to be what? It is your voltage Vs. In case of capacitor we always used to consider the same resistance across which we have to find, but in case of capacitor it is the opposite resistor, that is C2 upon C1 plus C2. Similarly in case of Vs it is C1 upon C1 plus C2. Very important formula, just keep in mind. Similarly I am writing for current I1 and I2. We will later see how we have solved it. It is Is into, that is C1 upon C1 plus C2, and it is Is into C2 upon C1 plus C2. So this is for current division. So whenever you have to find the potential across the capacitors just by applying a voltage division and a current division rule, this is your voltage division. Okay, this is your simply voltage division rule and this is your current division rule. So these are the value of voltage and current. Just by directly applying the formula one can easily able to find the voltage V1 with the help of this formula, V2 with the help of this formula. Okay, you know the value of C1 and C2, one can easily find these values. Similarly, when you know the value of current Is, you can easily find the value of I1 and I2 in case of capacitor. Very simple formulas, just keep in mind. Now, a question comes to your mind, how these formulas came, because in case of resistance, it is easy to understand. But in case of capacitor, how we have solved this and get these answers, we will see. So first we will see case 1 in case of voltage division. Keep in mind, when capacitors, see, when we are finding in this condition, that means the same current is flowing here. Okay, so as per the concept, whatever the charge appear at this capacitance C1 and whatever the charge appear at this capacitance C2, that is Q2, and when they are connected in series, so you can say that the value of Q1 and Q2 is equal. Very important. The value of Q1 and Q2 is equal. Q1 you can say that it is C1V1, Q2 you can say that it is C2V2. So from here you can say that C1V1 is equal to C2V2, or you can say that V1 upon V2 is equal to C2 upon C1. Okay, this is one formula. From here if you add, that is in this fashion, V1 plus V2 upon V2, that is C2 plus C1 upon C1. So from here you can say that the value of Vs is what? The value of Vs is V1 plus of V2. Yes. So just by putting this value here, you can say that Vs upon V2 is equal to C1 plus C2 upon C1. Okay, so since we have to find the value of V2, so the value of V2 comes to be what? It is C1 into Vs upon C1 plus of C2. So as I told you earlier, the value of V2 comes to be what? It is C1 into Vs upon C1 plus of C2. Similarly, you can find the value of V1 comes to be C2 into Vs upon C1 plus C2. Okay, so we just understand how we have find these values, that is V1 and V2. Now similarly we will see for case 2 also. Now we'll talk about case 2 when current source is present. This is Is, this is C1, this is C2. As I told you, the voltage here is V, this is I1 and this is I2. Okay, so from here you can say that the voltage appear across in this combination is V. Why? Because when the capacitors are connected in parallel, so whatever the voltage appear here will the voltage which is appear here. So if this V is the voltage, so you can say that Is is equal to C equivalent of dV by dt. So this is your equation first. Similarly, you can say that I1 is equal to C1 dV by dt, and you can say that I2 is equal to C2 dV by dt. Say this is second, say this is third. Now you have to find the value of I1 in terms of Is. Okay, so here the what is C equivalent? C equivalent, when capacitors are connected in parallel, the C equivalent comes to be what? That is C1 plus C2. Now you just put that value and find the answer. So from here we can say that we remove this dV upon dt from here and put this value in this equation and in this equation. Okay, so you can say that I1 is equal to C1 into, if I put this value, so it is Is upon C equivalent. Yes, yes, I have taken this value, dV upon dt is what? It is Is upon C equivalent. Simply I have put this value here. Okay, from here dV upon dt I have put here. Similarly, the value of I2 also comes to be what? It is C2 into Is upon C equivalent. Yes, so from here the value of I1 comes to be what? That is C1 upon C1 plus C2 into Is. And what is the value of I2? It is also C2 upon C1 plus C2 into Is. So these are the two values of I1 and I2. Okay, so from here we understand that yes, in this fashion voltage division and current division is applicable, and one can easily able to find the one can easily able to solve the numericals problem. Okay.